Okay, so let's begin by drawing the connection between the weighted average and the regular average. As we talked about this last time, I want to do a better version of that or a different version of that. I want to try it again. What is the equation for the weighted average? What is that equation? Yeah.
It's the summation of like all the weights times the value divided by the summation of all the weights.
Oh, wait, so the summation of the weights times the value. Wait, yeah. Is that what you said? Yeah. Make sure yeah. So sum of all the products. I equals 1 all the way up to n divided by, as you point out, the sum of all the weights. I equals 1 all up to n. Now, if all the weights are the same, or if we just say all weights are W, then logically, what must W be equal to? Yeah. The sum would be 1. But what would each individual weight be? The amount? So in other words, the number of observations, right? Which we had a term for. What letter is that? The number of observations is n. And it would be n over something? Couldn't we just say 1 over n? If there are 2 observations, then each observation has 1/2, right? If there are 3 observations, then each observation has a weight of 1/3. If there are 4 observations, 1/4, 5th observations, 1/5, etc., etc. Does everyone see that logic? So we can do some substitution. We're going to do this all the way up to n, 1 over n, I divided by summation, all the way up to n, 1 over n. Does everyone see that substitution I just did? I'll say if that is the same thing, then it's whatever. Okay. Can we simplify this? Yeah. Like for one, this is a constant, right? 1 over n is a constant, so we can do this. And what is this the same thing as? Yeah. We what? Well, oh, you want to put the 1 over n out here? We can do something even simpler than that, right? We could recognize that if you take anything, any single constant, and you add it together x times, so if you take 5, and then you add 5 together, I don't know, 30 times, what is that the same thing as? If I take 5 plus 5 plus 5, and I do that 30 times, what is that the same thing as? Multiplying. Right, multiplying. Or 5 times 30. No tricks here. So if you're taking 1 over n, and you're adding it 1 over n plus 1 over n plus 1 over n plus 1 over n, and you do that n times, that's the same thing as n times 1 over n. You take 5 plus 5 plus 5 plus 5 plus 5, that's 5 times 5. Right? Well, what does this simplify to? 1. So we can say, and we can put this in the denominator. We can say, so for example, We can do that, right? Right, which is the same thing, of course, as the average. Yeah.
Can you just quickly go over some of the results as like what in terms of like data set, what would be correct?
Like for right here?
Yeah. Full expression.
Okay. Yeah, let's unpack this expression. That's going to come up anyway, we do standard deviation. So the sigma is just noting that what follows is going to be added together. We can actually start over here. I put a parentheses because I wanted to indicate that a set of things is going to be added together. When there's no parentheses, of course, like right here, we just add all the W's together. We add all the N's together. All the N's that we got, in this case, NN's and W's. Here I want to be adding a product of two things together. So I put the parentheses in to emphasize that I'm going to be adding this result, right? It's going to be this stuff. And then they're next to each other because it's the first weight, I equals 1, the first weight times the first observation. The second weight times the second observation. The third weight times the third observation, and so forth. Okay. Each observation has its own weight. As mentioned, this is how you grade this calculator. If you take your homework, it has a weight of 1% or 0.01 or 0.01. 0.01 times the result of that homework plus 0.01 times the result of another homework plus 0.01 times the result of the second homework, so on and so forth. And then, like, you know, there's more weight on exams, there's more weight on the paper, even though everything's out of 100. Does that clear that up?
Yeah, so the end stuff, it's not that it's necessarily sequential, it's just whatever the group is for that particular.
Exactly.
Okay.
It's a way to map the weight with the observation together, to pair them.
Whichever one it is.
Yep. Great question. All right, so just to make sure we're all aware of it. And of course, you have all these products and then you sum them all up. Any other questions? Great. So that was the big thing we did. We also covered geometric mean. Right? We use that for growth rates. We do not use them for regular everything because growth rates are, for lack of a better term, weird. So, any questions? Okay. When I say dispersion, what do you think of? Like, what image comes to mind? Spread it out. So that. Yeah, tell me more. What do you mean? Sure. So if we think about how we measure dispersion, we think about how spread out the data is, right? And that's a great way to think about it. To spread out. Let's say how spread out the observations. The data are. The observations are. Data is plural. So we can also think about too, maybe in a lot of ways, it's measuring consistency. There are two basic ways to measure consistency, to measure dispersion. There is a simple way, and then there is a, we'll call it more complete way. The simple way is the range. It's just equal to the maximum value minus the minimum value. It cares about the largest value of the data set. It cares about the smallest value of the data set. Or what does it not care about? Yeah? Sure.
The middle, yeah, the between, exactly. That's the same thing, right? It doesn't care about the middle of the data set. It does not care at all about the middle of the data set.
And that lacking of caring about the data set is a problem with range, because it treats very different data sets as the same. So just to give you an example, a couple of examples. Imagine 3 data sets that have the same range. One data set looks like this with lots of observations here. One data set looks like this with maybe a bunch of observations here and here. And one data set looks like this. All of these have the same mean value, right? Same average. I try to draw it that way anyway. All of them also have the same range. But do they look like the same data set? Do they look pretty vastly different? Absolutely. A bunch of observations clumped together seems very different than them spread out like this. It seems very different than them sort of uniformly spread out. So it would be nice if we had a way to measure consistency that considered the values of each observation. Just like how mean considers the values of every single observation, and not just the order like median does, but the actual values. And we do have that. You probably know what it is. Does anyone know what I'm talking about? Anyone? Standard deviation. What is standard deviation? The whole variation of the data. No, it's always in the same units. As the data itself. So if you're looking at the standard deviation of income, then the standard deviation itself will be expressed in dollars or in euros or in yen. If you're looking at the standard deviation of people boarding an airplane, then that's going to be, standard deviation will be expressed in people. If you're looking at standard deviation of weight of cargo, then it will be expressed in terms of, standard deviation will be expressed in terms of like tons or pounds or kilograms or whatever. I want you to understand the math behind it. In practice, as you'll find out, Excel has it built in, so you never actually calculate it, but you should understand what's going on intuitively, how it is looking at every single value. It uses every value. To understand that, let's go over notation. This is notation we're going to be referencing throughout the semester. Generally speaking, we draw a distinction between population and sample. It's helpful for statisticians to have different notation indications for population versus sample, because sample mean is not population mean. Sample standard deviation is not population standard deviation. So we have mean, we have standard deviation, and we have size. Generally speaking, population involves Greek letters. Sample involves Latin letters. So sample mean is X bar. Population mean is mu. Mu. Has anyone seen that before? Mu. Excellent. Sample mean, a sample standard deviation, I should say, is S. Does anyone know what the the population standard deviation is? It is what? It's a Greek letter. Yeah?
Is it lowercase?
Okay, sigma. Nice. Does that look like a great sigma? No, it's hard to draw. But you get the idea. I know everyone wants to call it like it looks like kind of like an R, but it's lowercase sigma. Uppercase sigma again is the summation notation. Sample size, we've talked about this one. What is sample size? Anyone? N, specifically lowercase n. For some reason, population size is uppercase m. I never really understood why. Why don't come up with another Greek one? That would be nice. They didn't do that. I don't know the equations. Let's start with sample standard deviation. What we are going to do is we're going to want to look at the difference between the observed value, each observed value of the data set, and the average of the data set. So if the average is this, we want to look at the difference between that average and the value. The average and the value, the average and the value, the average and the value. Sometimes that difference is going to be huge, of course. Sometimes it's going to be small. That's the point.
Okay. Is that some issue? Okay. Okay.
So, the difference between the observed value, I don't know if you can see it all the way down here, but the observed value and the average. And then we square it. We square it because we want to give disproportionately more weight for things that are really, really far away than things that are kind of close by. It also has the virtue of making all values what? Begins with a P. Not percent. Precise, not precise. Positive. All values will be positive. And that's important because we're going to take all these now positive values and we're going to add them all up together. And I equals 1. Then we take this result and we divide by n minus 1. And then we take the square root. Do you have to memorize this equation? No. Because it's going to be on your exam, it's going to be on the last page, whatever. But you should intuitively understand what's going on. In other words, if there are lots of observations right near, well, let me ask you this. Which one of these three, A, B, and C, should have the lowest standard deviation? C. Why do you say C? Did you say C?
I said it.
C. Oh, okay. Okay.
It's in a straight line.
It's in a straight line, but think about what's going on.
So,
So Deborah, think about what's going on though. Because what we're going to do is we're going to take this value, and I want to let's imagine. Let's imagine the red line is the average. Let's imagine it's the same. So we're going to take this value here, and we are going to subtract off this, and then square that difference, and then this value, and square that difference, and this value, and square the difference. So a lot of these numbers are going to be pretty large. Some of them are going to be pretty small, but some of them are going to be pretty large, right? But now look at A. Are we going to have a lot of small values or a lot of large values? We have a lot of small ones, right? Because a lot of the bulk of the observations are huddled around the mean. And because of that, there's going to be a lot of differences here that are pretty small, which are then squared, which then add up to something pretty small. Granted, there's going to be two observations that are pretty large, but they all have that. A will have the lowest standard deviation, but will have the highest standard deviation. B, why? Yeah, everything's going to be a large value, right? Every one of these things is going to be a large value. And then C is going to be somewhere in the middle. And not how well that balances with our intuition. But this one seems to be the most consistent, right? Most of the observations are right in the center. B seems to be the least consistent. They're wild in each direction. This one is kind of halfway between the two. So that's pretty good. Make sense? We good? All right. We also have an equation for the population standard deviation. This one does not come up very often, but I want you to know what it is because Excel gives you options for both, and so I don't want anyone to be confused. Mathematically, it looks very similar to this. There's only one minor mathematical change and a couple of different notation changes because it's the population. We still take the square root. It's not the nth root, it's just the square root. We still sum up differences between the observed value and the mean, but now we're using mu instead. We still square those differences. We use mu, of course, because we're working with the population. And we still divide, except we don't divide by 1 over n minus 1, we just divide by 1 over n. And again, I'm going to capital N because it's a population size, not a sample size. So you see, mathematically, there's very little difference between these two. There's just a slight difference in division. But I want to draw your attention to that because you will see in Excel, you will have two different options, and I want you to always select this one, sample.
Because in practice, that's what you're actually getting sample size. Any questions?
Great. So let's go work with Excel a little bit then. Go with my teaching, go into BSAD 210, and let's pull up R for N data set 2. So we call data set 2 covers what kind of data? Amanda, what kind of data does data set 2 cover? Yeah, what's the thing that pops up? Sales for whom? Disney. And so we talked about like who has the best average sales, finding the geometric mean, etc., etc. By the way, I discovered that you can also find the geometric mean if you do the regular mean, you highlight, you add 1, which I told you weren't supposed to do, subtract 1, but this will work. That method will work.
This method will work if you then
now press Control, Shift, and then holding Control and Shift, press Enter, and it will give you the result. It won't give you an error message. And you can see at the top here the brackets to put in. I've tried putting them in myself. It doesn't like that. But if you hit Control Shift Enter, then it will do it. You won't have to use like that weird sum product thing we had to do. I don't care what you do on exams as long as you make it clear what you did. And I don't throw in the brackets to let me know when you're justifying things that you hit Control Shift Enter and you know what you're doing. Or just mention you hit Control Shift Enter. But I thought that was a pretty cool trick. That's 100%. So there we go. And then of course we can get it for everything. But let's imagine we don't necessarily want this. Let's imagine we want to know which is most consistent. We want to get an idea of dispersion. So there's a couple of ways we can do that. Let's get the range. Now, what does the range equal? What is it equal to? The max minus the min. So how do you think we can figure it out? What's the secret to Excel? Equals. So let's press the equal button and I don't know, type in range. It doesn't come up. It gives us a random number option, so we can't do that. Nope. But we can remember that range is max minus min. So what can we do? If I wanted to figure out the range of this data, what can I do? So, and you can do this, so often in data sets, you're asked to report, and it's common to report the maximum value of your data set and the minimum value of the data set. So that people can just visualize, they can easily see the range. We're just gonna do that all in one step. So let's type in, I wanna get maximum. What do you think I type in? Max. There it is. And then we're just gonna highlight these values right here. And then what do we do? I like that you said close parentheses. Yes, close the parentheses because we're going to add in a second equation, the min, and then we can just highlight this as well. Is that what you're thinking, Amanda? Just highlight it? Excellent. And now we can hit enter, and it's going to be like, we found a typo. And it's like, well, I know what the typo is I just didn't feel like adding that. Yeah, I'll accept the correction. I'm making you do the work. And now we have a range. What is this range? Or about 2.9 billion. Remember, this is in millions. Excellent. Let's do quartiles. I'm going to highlight this 5 area here and hit merge and center. Ooh, I don't like that at all. Let's put it in the middle. There we go. I'm going to call this quartile. Because I want the 0th, 1st, 2nd, 3rd, and 4th quartile. What are the quartiles? What is a quartile defined as? 25% of the data. All right, Oscar is absolutely right.
Just realized I might not be able to see that. That's a short share.
So we can think about 25% of the data. This also gives us a sense of how the data is dispersed. Because if the upper and lower bounds of a quartile are next to each other, then that suggests there's a lot of concentration there because that has 25% of the observations. If the quartiles are really far apart, then that also suggested something about the dispersion. It's like a subset of ranges. It's like we're going to create, 4 different ranges within the data. And the range, rather than encompassing all the data, only encompasses a quarter of it. How do you think that we get quartiles in, Alexia? How do you think that we can put quartiles in? Well, what's the secret to Excel? Equal and type vaguely what you want, right? So what do you think we should type in? You know what to type in, I just said. What are we looking for? Quartile. So what should we type in? Quartile. When in doubt, just type vaguely what you want. I don't know, quartiles. Is that? Oh, look at that. We want to go with the included option.
Because I have my notes based on
an older version of Excel, and you see just the quartile option in there with the little yellow triangle. That means it's supported by an old version of Excel. But they expanded your quartile options. We're going to use the INC, the included one. And then we're going to highlight this area. And this is one of those things like sum product where it needs more than one input. So I told it what it wants to look at, the data it's curious about. And then I need to tell it what quartile it wants, comma, which quartile. And note, so we can do 0, and that will give us the minimum. I can just type in 0, or I can highlight this range right there that I had put in before. Or not the range, the 0th quartile, right, under C24. And that gives us the lowest value. Note the first quartile, the 0th quartile is always defined as the minimum. Similarly, I could type in quartile, inclusive, highlight this area, comma, 4, and get the largest quartile. And by definition, the largest quartile is the maximum. If you take the maximum minus the minimum, you get the same thing as the range. We good? Now, if I want to do this for all of them, can I just drag this down and get them all? No, why not? So now here's my challenge for you. What I want to do is I want to have it both ways. I want to type in one thing. I want to be able to copy and paste this one thing down so that it will update the red one will update 1, 2, 3, 4. But I also then want to take this block and be able to copy and paste it over here to F and H and J. And it will not move this column over. So the blues will update, but the reds won't. Do everyone see what I'm trying to go for? Does everyone see what I want to do? I want to make it so that when I copy and paste it down, the red changes, but the blue doesn't. And then I want to make it so that when I copy and paste it to the right, the red does not change, but the blue does. Can anyone think about how we can do that? It's my little challenge for you. So we can do F4, but if we hit F4, as you will find out, let's do it right here. And let's do it right here. That will lock it. And that's good for when I go down. When I go from like 0, 1, 2, 3, 4. But it will not be helpful when I go to the other sectors because it will just keep referencing the other sectors. You know, it'll reference this first one. It'll keep referencing studio over and over again, right? I don't want that. And this didn't even stay put either. I don't want that. In fact, if I lock everything, then it's always just going to be that thing, that result. And that is emphatically not what I want, right? I don't want this always to be 528, and then it's always 520. That's 5,825. I don't want that. Remember what these do. What do these dollar signs do? Yes, exactly. Yeah, exactly. So does everyone follow that? So then, just for those who didn't follow it, recall there are two dollar signs because there are two things being locked in place. One is the column and one is the row. Sometimes I want the row to change, but not the column like I do with red. I want to be able to go down, but always, if I copy and paste it to the right, I want to hold the column. So in that case, I will lock the column, but not the row. I will lock the column, but not the row. That way, as I copy and paste this down, you see the rows update. But when I copy and paste it to the right, it does not. Similarly, I want to lock the rows, but not the columns for blue. I want to be able to keep this same range up here, but be able to move it over as I go to the right. So I will remove the dollar signs next to the D. Now, when I copy and paste it down, and then I get that whole thing, oh, let's actually do this. And then as I copy it to the right, I now have quartiles for everything. And you just pick one at random, and you'll see it's highlighting the stuff you want it to highlight. Isn't that cool? You guys don't care. I'm going to assume that your silence is just flabbergasted astonishment. But now what we have is we have quartiles for all of our different data. And we can see kind of like what the dispersion is within these different quartiles. Like this is really close together. Like this is really close together too. Look at that. The first and second quartile. As a side note, what is the second quartile? What is it also known as? The median, yes. All right, any questions? Yeah? Yeah, I'll delete it all and I'll do it again, no problem. Yeah, we got time. Okay, let's delete all this. So, and let's just, oops. Do you have this, basically? For those who didn't follow? Yep. So, when I have it locked right here, no matter where I copy and paste it, I'll get the same result. Because this is always going to reference, because red is always going to reference here, blue is always going to reference here. I would like to be able to say when I go to the right, this holds in place. Right? Sorry, this updates. Blue updates. But when I go down, blue does not update. It doesn't scoot down with it. So that means I want to hold the rows constant. I want to lock the rows so they don't scoot down. But I do want to unlock the columns so they do scoot over. So those dollar signs with a just to the left of a number or letter means they are locking the thing to there to the left of. So I can do this, and I can do this. And now when I copy and paste it to the right, it will update blue, but when I copy and paste it down, it will not update blue. When I change the columns, it will change. When I change the rows, it will not change. And I want to do exactly the same thing, but opposite for red. I want to be able to say when I go down rows, red changes, but when I go over columns, red does not change. And therefore, when you're comfortable, you can type in just that one thing, and then you just do a lot of copy and pasting. And then you did the whole thing. Pick one at random, it will be doing what you want. Oh, hey, we can do this one too, as long as we're after it. Let's just throw this over here. There we go. Okay. Any questions? And I'll show you your formula. And then just log C. Yep. And then copy paste down, copy paste over.
Yeah, highway estimate presentation.
Let me give you one. So you can see what I did. There you go. Are we good? I think we're good. We got other things to talk about. We haven't actually calculated standard deviation. Now let's calculate standard deviation. Okay. Oh, that's ugly. Let's make that bold. Bold, there we go. I usually abbreviate it STDEV. But of course, Excel also has standard deviation built in. What do you think we typed to put standard deviation in? Anyone? Yeah, when in doubt, just start so if we should have been standardized, which we don't want. What do you think we do? But STDEV does indeed look like standard deviation. That is the abbreviation. and you see it has a dot P and a dot S. Which one do you think we use? S, exactly, because that's for the sample. All right. And now we just highlight the stuff we care about. Let's expand that a little bit. And we can get standard deviation for everything. If you want to, if you're curious, you can look at standard deviation of the percent. Of course, because it's a percent, it's going to make it a 0, so you can throw that in. If you're curious. I'm going to set it aside though for now because I want to focus on what we're working with here. Okay, so my question for you, oh, I forgot to do this because this is going to be annoying. Let's freeze our section so we can see what's going on here a little easier. Freeze the panes. There we go. Now my question for you, now we can see everything nicely. Which sector, excluding the total, which sector do you think is the most consistent? Which sector do you think is most consistent?
Absolutely. After that's the lowest standard deviation, so it seems to have
The least spread. And that's a great starting point, but we have a little wrinkle in that I want to draw your attention to. And to show you that wrinkle, let's switch to biology. How tall is the average person? Generally speaking. Generally speaking. So male and female. Human. Average 5'6". Yeah, globally, I would say. Now, standard deviation is hard to estimate. That's one of the problems with standard deviation. It's not intuitive. You know, you really have, it's like great for comparison purposes. That's a high one. We know it's high because the other ones are lower. That's a low one. We know it's low because the other ones are higher. But by itself, it's not super intuitive. But what is more intuitive is range. That's one of the great things about range. It's easy to estimate. It's really intuitive. What's the range of human height, generally speaking? Like how short are the shortest people, generally speaking? 3 feet, right? Maybe around there. What do you think the tallest people are? Maybe 7 feet. So we're talking about maybe something that has like a range of maybe about 4 feet. I think 3 is I'm not exactly sure how low it gets or how high it gets, but maybe 4 is about right. And maybe the tallest person too is even taller than 7. Now, here's the biology part. What do you think the average is for ants? Like how big, how long is the average ant? I think that might be like a full centimeter, right? I've seen some pretty big ants.
I've seen some big ants.
We can do like half. Does anyone want to say half a centimeter, 1 centimeter? What do people generally think? You want to do half a centimeter? We can do a centimeter. I mean, termites aren't ants, I don't think. I don't know that much biology. I don't think they're ants. But we can, just because 1 centimeter is a little easier. But now, how big is the biggest ant you've ever seen? Like the quarter size? That's probably, what, like 3 centimeters? Like the biggest ant you've ever seen? Probably 3 centimeters. Right, do we agree with that? What's the smallest ant you've ever seen? So we can reasonably say that maybe the range of ants is somewhere along the line of like 3.9 centimeters. It's the smallest you've ever seen as a millimeter. I don't know if those are babies or not, because again, I don't know that much about biology, but let's just assume that maybe that's the case. So we have ants that are range almost a 4 centimeter range versus a 4 foot range. Which animal has a more consistent height/length? The answer want to say more consistent, right? Why do you say more consistent, Mark? Yeah, like well, this is only 4, and this is only 4 centimeters. This is 4 feet. So you want to say this is more consistent, right? This is clearly smaller. But does that make sense? Does that seem kind of weird? Why do you say it's kind of weird, Michael?
Because it's like, I mean, it's more like based on like the context of it, because like, 4 feet per range for humans doesn't seem that bad. 3.9 centimeters for range doesn't seem that bad for ants either.
Well, this seems huge to ants, right? And this doesn't seem that big of a deal. This seems huge. Like you're right, context matters. On one hand, it seems like ants are more consistent because their standard deviation is much smaller. The range is much smaller. Their standard deviation surely would be too, compared to humans. But think about it from the ant's perspective. Like sometimes I see an ant that's like half my size. Sometimes I see an ant that's 3 times my size. Do you typically see people that are like 15 feet tall? Right? No. So at some level, looking at the raw standard deviation is deceptive because it doesn't put it into context of what you're actually looking at. It doesn't put it into context of the average. I'm looking at just looking at standard deviation. And that's what I mean by raw standard deviation. I'm like just looking at standard deviation out of the context of what you're actually drawing from. It can throw things off. Like, let's say like a small town has a budget shortfall of like $100 million, or a standard deviation of say $10 million for its budget. That seems like that's much more inconsistent than if the U.S. federal government had a standard deviation of 10 million. Right? Even though they're both $10 million, right? That one is clearly a larger swing from the perspective of the small town versus the perspective of the U.S. federal government. Right? 10 million is like what the State Department spends on post-it notes. Right? It's like 10 million is nothing, but 10 million for like a small town, that's huge. So we want to really get a good idea of what's consistent and not. We want to take that standard deviation and we want to put it in the context of the average. And we do that with something called the coefficient of variation. Essentially, we are asking,
take a look at that standard deviation. What percent of the average is it?
What percent of the average is the standard deviation? In other words, it is the standard deviation divided by the average, and then we throw in times 100%. This is technically the standard deviation of the coefficient of variation of the sample. There's another one for population that just uses sigma and mu, but it's the same calculation. This is a better measure of consistency. This is a much better measure of consistency. Any questions? So let's do it. I want to put in coefficient of variation. That's kind of a long word, right? There's like 3 words in it, actually. It's 3 words. So I'm just going to put in COV. And we'll bold it too. Now, here's the thing. Excel does not, at least to my knowledge, have coefficient of variation built into it. Covariance. That's not what I want. Okay, well, whatever. So it doesn't have it. But luckily, the equation is super simple. How do we think we find it? Yancy, is Yancy here? Yes, Yancy. How do you think we find it? How do we find the coefficient of variation using the information that I have here on the board? What's in the numerator? Standard deviation. Do we have standard deviation? Because it's right here, right? Yeah. So let's start by selecting that. Then mathematically, what do we do? Sarah, what do we do next? Divide it by the mean. Oh, I forgot to put the mean in. Well, that's okay. You know what to do, right? Okay, so help me out. What do I do? What should I do? Well, we already have equal. I put in standard deviation numerator. I'm now dividing, and then I need the average. I don't have the average in a separate cell, but what can I do? No, we don't need to use the geomean. Just, when in doubt, if you want something, what do? You just type it. Yeah. So we just type an average, and then we highlight. Oops, I don't want to highlight that part. Here we go. And when you hit, are we good? So again, I could, if I wanted to, create a new row and call that average, and then said this is the average, and then do 1 divided by the other. The nice thing about doing that is then we get to see the average, which is one of those basic bits of information. But I didn't feel like doing that this time, so we just did this. Oh, I got 0. What do I do? Yulia, what do I do? That's true, I can do that. So I can multiply it by 100. I can do that. Or I could have Excel do that for me by doing what? Anyone? I was thinking hit the percent sign. Because hitting that percent sign is functionally multiplying it by 100. Not only multiplying it by 100, multiplying it by 100%. And now if I wanted to, as mentioned, I can throw the decimals in and maybe see what's going on. Everyone get that? 11.6%. The studio's standard deviation is a little over 10% of its average. And now I hear a lot of beeping sounds, a lot of dings. So I'm just I'll throw this up here so you can see what I did. Okay. No, yes.
Do you mind explaining the deviation as a common?
So the coefficient of variation is referencing the mean. And so that means that then is the standard deviation higher because it's less consistent, or is the data less consistent, or is it higher just because the mean is higher? Well, by throwing the mean in, then we can pull out that declaration. So now, with this in mind, you can tell me which sector is most consistent. Again, the going tool. Which Which of these sectors is most consistent? Remember, a low value, a low coefficient of variation means more consistency. A high coefficient of variation means less consistency. Wilder. So honestly, what's on it? Which one is the most consistent? There's a bunch of us. Okay, you can decide. Studio. Why do you say it's studio? Exactly. Even though studio standard deviation was 733, which was kind of in the middling range of standard deviation, its box office average is so large that in reality that is actually a pretty low standard deviation. That's actually a pretty consistent value, right? Its coefficient of variation is the lowest one, even though the standard deviation was middle. You picked, what did you pick for the most consistent? The first time around for standard deviation? Interactive. But in reality, interactive is what? The least consistent. Right? It had a low standard deviation, not because it was very consistent value, but just because the averages were so low. If you look at it, it's actually very inconsistent. Right? Look at this. Look at this. 1 year it's like has a 29% growth. And then the next year, it like lost 14%, and then it gained 26%, almost 26%. This is kind of wild. Plus, in part, it's, oh, this was 78. Look at that. One of the reasons why it's so inconsistent is because it's clearly a new sector, right? This goes back to like the 90s, the late 90s. How did I? Okay, whatever. But it is still like, but still, I mean, that's how the numbers are coming out. Yeah.
So we're not using the geometric mean for this, right?
No, because we only use the geometric mean to calculate average growth rates. I think I screwed up my freezing panels. There. I meant to do that one. Okay. Any questions? Any other questions? So actually, it is the least consistent. It is the most unpredictable. Its standard deviation is more than half of its average. That's huge. Okay. 2 very minor points. I'm not going to really make a big deal about these for exam purposes, but I do at least want you to be familiar with this terminology, just to get it in your head, because it's just going to come up as part of the terminology of going through equations and seeing different parts of stats. You'll note that in this equation, we took the square root. If you don't take the square root, in other words, if you square standard deviation, it's just called the variance. That's just standard deviation squared. It's typically called, you typically see it as just S squared. Similarly, standard error is just S divided by the square root of the sample size. Again, that is an equation that comes up a lot. So that's just the name for it. I'm not going to necessarily test you on this terminology for the upcoming exam because it's kind of just a side note. But I put it in the notes. I want you to at least be aware of this terminology, because sometimes that comes up. But in the process of studying for like the exam, don't prioritize memorizing these two things. Like, it's cool if you do, but I can simplify this a little bit. Variance is just standard deviation squared, and standard error is just S divided by.
Okay, that's all I have for today.
I will see all of you on Thursday.